All right, so in this video, I'm going to talk about the root test, which is one of two main tests that we have to help us analyze sequence or a series whose terms either grow or decay at least exponentially quickly. And what I mean by that, I'll make a little bit more clear at the end of this video and in the next one. But so let me just state the formulation here. And again, this is probably something you've seen before, although now that we have the language of lim inf and lim sup, these statements actually will become a little bit more powerful than probably the versions that you've seen in the past. So here we go. This is 14.9. So the statement is this: let an be a series and set alpha equals the lim sup of the absolute value of an to the 1 over n. Then there are three cases. If alpha is less than 1, then the series converges absolutely. If alpha is bigger than 1, then the series diverges. And in the third case, if alpha equals 1, we get no information. So the series could converge, it could diverge, we just have no idea. And so this should kind of make sense because basically, if alpha is less than 1, then that means that, like, at worst, the terms an look similar to alpha to the n, right? And we know that if we sum up a geometric series, right, if the base of the exponent in the terms of the geometric series is less than 1, then the series converges, right? And similarly, if the base of the exponent is bigger than 1, the series obviously diverges. Like if you sum up 2 to the n, it's going to be, you're going to get infinity pretty obviously, right? And then here, this case is a little bit more subtle, and we'll talk about it once we get there after we prove the first two cases. So let me just start to go through the proof here. So in case 1, so this is the proof of the root test. So in case 1, suppose alpha is less than 1, right? Then pick epsilon greater than 0 such that alpha is less than, alpha plus epsilon less than 1. Okay, all right, sorry, I had to make an edit. But yeah, alpha plus epsilon is basically just this number that we're going to be using to form an upper bound on the overall series of an to be able to bound it above by a convergent geometric series, basically, and use the comparison test, right? So this is actually, we're going to see a common thing. So we will show that the series of an, let's say absolute value of an, from n equals 1 to infinity, converges by showing that the series from n equals capital N plus 1 of absolute value of an converges for some n. Okay, and the plus 1 here is actually unimportant. It's just the way things work out in the proof. You end up with this plus 1, but it really doesn't matter. The point is, the conceptual idea here is that if you just show that basically what we would call a tail of the series, so if you just like add up all the terms of the series beyond a certain point, if you can show that a tail of the series converges, then that automatically means that the entire series converges, because to get the original series back, all you have to do is just add in the first capital N terms here. And so obviously that's only a finite number of terms, so it can't affect the convergence, right? So if we can just show this converges for some sufficiently big capital N, then we're good. So so note, since alpha is less than alpha plus epsilon, we've seen this before. The book kind of explains this, you know, in a slightly more convoluted way, but we've seen this a number of times by now, that that we can only have absolute value of an to the 1 over n being bigger than or equal to alpha plus epsilon for finitely many values of n. Right. So there exists a capital N such that an to the 1 over n, right? This is because alpha is the lim sup of these, right? So just remember, this goes, we actually did kind of an example. There was a discussion about this, I think, in the lecture about section 12 in the textbook, where we talked about like whether there can be finitely many or infinitely many terms of a sequence being, you know, above or below the lim sup or the lim inf or whatever, right? So here, you can't have infinitely many terms of the sequence be greater than alpha, right? So basically, there can only be finitely many that are greater than or equal to alpha plus epsilon. So there exists an n such that this is less than alpha plus epsilon for all n greater than capital N, i.e. absolute value of an is less than alpha plus epsilon to the n. Okay? So now we can use the comparison test to argue that because this converges, right? So since the series from n equals capital N plus 1 to infinity of alpha plus epsilon to the n converges, then the series from n equals capital N plus 1 to infinity of absolute value of an converges as well. So then by this logic up here, right, we showed that this converges, so this overall series converges, right? So the sum from n equals 1 to infinity of the absolute value of an converges, meaning that the sum of an converges absolutely, as we wanted to show. Okay, so that's the first part here. Really not too bad. And see, look, we really are using the intuition here that the root test is one way of kind of using geometric series as like a frame of reference to analyze our sort of, you know, a more possibly more complicated series, basically. Okay, so now for part 2, suppose alpha is bigger than 1. This means there are infinitely many n such that absolute value of an to the 1 over n is greater than 1, right? But then there are infinitely many n such that an itself is greater than 1. So clearly, the terms an do not converge to 0. So the sum of an has to diverge, right? Remember, this was an early corollary, I think it was corollary 14.5. This was an early fact we established about series, that in order for the series to converge, we must at least have the terms approach 0, right? Of course, that's not enough to make sure it converges, but if the terms themselves don't approach 0, then obviously the series itself can't converge. So in this case, we see that the terms do not approach 0, so the series must diverge. And lastly, we actually should prove that there really is nothing we can say in the case that alpha equals 1. So basically, we should give an example of a series where alpha equals 1, which converges, and a series where alpha equals 1, which diverges, right? So maybe actually it would be good for you to just pause and take a second to think about it. Obviously, if you want the answer, you can look in the textbook or whatever, or you can just like wait. This is not a lecture question, by the way, but yeah, it could be a good exercise for you to just think about. So in this case, basically the series that we use, the most common examples of this are something like, the series 1 over n diverges, and 1 over n raised to the 1 over n power approaches 1, okay, as we've seen, because n raised to the 1 over our n power we know approaches 1, right? So alpha equals 1 in this case, but 1 over n squared converges, and 1 over n squared to the 1 over n power also approaches 1. So alpha equals 1 in this case as well, right? So there are series which diverge and series which converge where alpha equals 1. And the key here is that these terms do not decay fast enough for the 1 over n, for the nth root to detect any sort of exponential change, right? So like these are like polynomial functions in n in the numerator and denominator here. And anytime you have something like that, the root test is going to be useless because these expressions just don't change fast enough, either growing or decaying, right? They don't grow or decay fast enough. They kind of stay relatively constant relative to like an exponential function, right? So that's kind of the moral here. So the root test is only useful for sequence or series whose terms grow or decay at least, exponentially quickly. So something like, the series of n to the minus n, right? N to the minus n is clearly, it's not an exponential function because the base here is not constant, right? It's actually n being raised to the nth power and then taking 1 over that. But this, so actually also like something like, 1 over n factorial also helps, or also works, except this one, it's better to use the ratio test. But this one is an example where you can use the root test to easily see that this series converges, even though it's hard to figure out what the value should be. And it's not a geometric series. These terms don't change exponentially. They actually change faster than exponentially. So yeah, the root test is useful there. Not so much for things like, n or n squared, or like anything random, like 1 over n to the 5th minus 3n squared plus 7 or something. You'll not get any information from the root test for something like that. So that's the root test. And in the next video, I'll talk about the ratio test.